Let's talk about plane curves and parameters. Now what parameters are is they are oftentimes values like theta or t, and they add a separate dimension to our problems, even if we're in a two-dimensional space. For instance, if you've got a parabola and you want to deal with a parabola and figure out which direction it's going, you could put a parameter in and that would help. So let's talk about that. This is plane curves. So we're talking about things on a plane, but we're adding this third dimension. So the definition of a plane curve is this, that x is equal to a function of t. T is oftentimes interpreted time. Y is another function of time. Now you could have theta or whatever, but it just adds a third dimension. By definition, a smooth curve is one that has f prime of x, g prime of x, and f prime of x, defined, and not zero at the same time. Except possibly at the endpoints. So if I've got something that is zero for f prime and t prime, then I could just talk about the values to the left of that and to the right of that, and I could call it piecewise smooth. All right, so smooth is defined here. So we don't want to simultaneously zero at the same time. Simultaneously and at the same time mean the same thing. All right, so what are some activities that we do with parametric or plane curves? Well, one thing is we might take a regular curve, so take a function, and it doesn't even have to be a function, but take a function y equals f of x and introduce a parameter. Now that is not a unique situation, so if you're ever asked to do that, you could get a different answer than everyone else in the room and still be correct. Let's look at an example. Let's say y equals x squared. That's a parabola. I'm going to define this a little bit differently. I'm going to say we're going to let x equal f of t, and I'm going to call that 3t. Then I'm going to say that y is equal to some other function of t. Now the thing is, I've got to keep x squared equal to y. So y would be 3t squared. So y equals x squared, but I just introduced that extra value in there. So we are going to get the same graph. This is going to have a little bit of a direction. And also, we could actually say that it starts at time zero, say. So we just introduced a parameter. Now that is not unique and may not even be useful in this case, but we put a value t in there and it relates the same way. Another thing that we might do is we might eliminate a parameter. And that's a little bit of algebra usually. So if we need to eliminate a parameter, let's take a trig question. Always kind of fun to work with a trig question. Say we've got x equals the tangent squared of theta and y equals the secant squared of theta. Well, I remember from trig that 1 plus tangent squared of theta equals secant squared of theta. And so these guys are related. So what I could do is I could put y here, and I could put x here, and have 1 plus x. So here's my function. Y equals 1 plus x. Now, did that look like that? Not at all. Okay, not at all. But y is equal to 1 plus x. I eliminated the parameter. The theta is gone. And the trig functions are gone, actually, too. Let's take another look. And I've got another trig function. Here's one that's got x is equal to h plus a secant theta. Y equals k plus b tangent theta. Now that one's not quite as simple as the last one, but let's see what we can do. If I take x minus h, I get a secant theta. And if I take y minus k, I've got b times tangent theta. They both have secant and tangent like the last one, but they're not related quite the same, I don't think. So let's see what happens. What we could do next is we can try to get rid of theta. Now, not necessarily always the easiest thing, but I know this is 1 over cosine. So if I multiply both sides by cosine of theta, I get this. I get cosine of theta multiplied by x minus h equals a. Or cosine of theta is equal to a over x minus h. Now I have this. I could say that this is sine theta over cosine theta. So multiply both sides by cosine theta. And here I've got cosine theta times y minus k is equal to b times the sine of theta. So I had sine over cosine. Now cosine theta is this, all right? So I could say, all right, this is a over x minus h multiplied by y minus k is equal to b times the sine of theta. Now I don't have the theta gone yet, but you notice that we're headed toward that. Now another thing that I want to do is I want to look at this. I like trig, so I'm going to do something with this. Cosine is adjacent over hypotenuse. So I'm going to build a triangle in the first quadrant. Here is my theta. And so if this is the adjacent side, it's a, and here's the hypotenuse, which is x minus h. So what's the opposite side? Well, a squared plus this one squared is equal to this one squared. So I know that a squared, this is y, I guess. I better not call it y because this has got y in it. So let me call it t, okay? So a squared plus t squared equals x minus h squared. So what's t? Well, t squared is x minus h squared minus a squared. So t is the square root. And you could say plus or minus, but a lot of times in this kind of trig manipulation, we don't worry about minus. So there's t, okay? T is the opposite side. So I'm going to put that and the hypotenuse in for sine t, or sine theta. So here I'm going to put this. I'm going to put square root of x minus h squared minus a squared, it's all under the radical, over x minus h. And look at that, I got rid of theta. Now, does it look nice? No. Do I have it solved for y? No. But is it did I eliminate the parameter? Yes. So that's the point in this. Let's take another couple of looks at some problems. Now, one thing that you might do is you might try to graph. And there are some things about your calculator that are very nice. So let's use the calculator and let's graph x equals 2 theta minus the sine of theta, and let's y equals 2 minus cosine theta. I'm going to use ATI 84 and put it up here. So here's my calculator. Here's what we need to do. Let me move it so you see all the functions. Okay, so I've got to first of all hit the mode button and put this in radians, and I need to put it in parametric mode. There's parametric mode, so that's important. The parametric mode, if I go to the y equals to graph, is automatically considered t, and it's a capital T here. I don't know why, but it is. So we're going to say that x is 2t. Notice the variable button. The second one is for parameter, so there it is, 2t, minus the sine of theta. So sine of, and I'm going to have to use t here, so sine of t. And then the y function is 2 minus cosine of theta. So there it is. Now, if we look at the window, so let me pop into the window. Notice now I've got a window that has t values. It introduced t. And t, the automatic part of the calculator starts at t equals 0 and goes to 2 pi. So 0 to 2 pi. And this step is how often it calculates. So that's, if you make that number super small, it'll take the calculator a long time. If you make it big, it won't be very accurate. So this is kind of a set thing in the calculator. I've got x and y from minus 10 to plus 10, and that may or may not give us a good graph, but here's what we get. Pretty exciting, not really. Notice it only graphed one side because t was positive, and we could stretch it out a bit. So let me change the x value to something like 25, and let's see what happens here. So there is what's going on. So that's basically the whole graph. Sometimes the calculator gets a little bit wimpy at the ends, but it looks pretty smooth. You could test the derivatives and see if it actually is. But your calculator will draw parametrics quite simply, and you've just got to put t in there. So that is something that might be a good plan.